This section describes trait objects in detail. You will also develop the world's next best-selling fantasy role-playing game, the RPG project. If you would like to focus on networking, feel free to skip ahead to section 8.4. There is a reasonable amount of jargon in the next several paragraphs. Brace yourself. You'll do fine. Let's start by introducing trait objects by what they achieve and what they do, rather than focusing on what they are. Section 8.3.1. What do trait objects enable? While trait objects have several uses, they are immediately helpful by allowing you to create containers of multiple types. Although players of our role-playing game can choose different races, and each race is defined in its own struct, you want to treat those as a single type. A vec of T won't work here because we can't easily have types T, U, and V wedged into vec of T without introducing some type of wrapper object. Section 8.3.2. What is a trait object? Trait objects add a form of polymorphism, the ability to share an interface between types, to Rust via dynamic dispatch. Trait objects are similar to generic objects. Generics offer polymorphism via static dispatch. Choosing between generics and type objects typically involves a trade-off between disk space and time. Generics use more disk space with faster runtimes. Trait objects use less disk space but incur a small runtime overhead caused by pointer interaction. Trait objects are dynamically sized types, which means these are always seen in the wild behind a pointer. Trait objects appear in three forms: ampersand dyn trait, ampersand mute dyn trait, and box of dyn trait. The primary difference between the three forms is that box of dyn trait is an owned trait object, where the other two are borrowed. Footnote 1. In old Rust code, you may see ampersand trait and box of trait. While legal syntax, these are officially deprecated. Adding dyn keyword is strongly encouraged. Section 8.3.3. Creating a tiny role-playing game, the RPG project. Listing 8.4 is the start of our game. Characters in the game can be one of three races: humans, elves, and dwarves. These are represented by the human, elf, and dwarf structs respectively. Characters interact with things. Things are represented by the thing type. Thing is an enum that currently represents swords and trinkets. There's only one form of interaction right now: enchantment. Enchanting a thing involves calling the enchant method. Footnote 2. Naming is hard. When enchantment is successful, thing glows brightly. When a mistake occurs, thing is transformed into a trinket. Within listing 8.4, we create a party of characters with the following syntax. Casting a spell involves choosing a spellcaster. We'll make use of the rand crate for that. The choose method originates from the rand seq slice random trait that is brought into scope in listing 8.4. One of the party is chosen at random. The party then attempts to enchant the object it. Compiling and running listing 8.4 results in a variation of this. The following listing shows the metadata for our fantasy role-playing game. The source code for the RPG project is in this file. Listing 8.4 provides an example of using a trait object to enable a container to hold several types. You'll find its source in this file. Trait objects are a powerful construct in the language. In a sense, they provide a way to navigate Rust's rigid type system. As you learn about this feature in more detail, you will encounter some jargon. For example, trait objects are a form of type erasure. The compiler does not have access to the original type during the call to enchant. Trait versus type. One of the frustrating things about Rust syntax for beginners is that trait objects and type parameters look similar. but types and traits are used in different places. For example, consider these two lines. Although these both have something to do with random number generators, they're quite different. Rand RNG is a trait. Rand RNGS, thread RNG, is a struct. Trait objects make this distinction harder. When used as a function argument and in similar places, the form ampersand dyn RNG is a reference to something that implements the RNG trait, whereas ampersand thread RNG is a reference to a value of thread RNG. With some time, the distinction between traits and types becomes easier to grasp. Here are some common use cases for trait objects. Creating collections of heterogeneous objects. Returning a value. Trait objects enable functions to return multiple concrete types. Supporting dynamic dispatch, whereby the function that is called is determined at runtime rather than at compile time. Before the Rust 2018 edition, the situation was even more confusing. The dyn keyword did not exist. This meant that context was needed to decide between ampersand RNG and ampersand thread RNG. Trait objects are not objects in the sense that an object-oriented programmer would understand. They're perhaps closer to a mix-in class. Trait objects don't exist on their own. They are agents of some other type. An alternative analogy would be a singleton object that is delegated with some authority by another concrete type. In listing 8.4, the ampersand enchanter is delegated to act on behalf of 3 concrete types. Section 8.4, TCP. Dropping down from HTTP, we encounter TCP, or Transmission Control Protocol. Rust's standard library provides us with cross-platform tools for making TCP requests. Let's use those. The file structure for listing 8.6, which creates an HTTP GET request, is provided here. The following listing shows the metadata for listing 8.6. You'll find the source for this listing in this file. The next listing shows how to use the Rust standard library to construct an HTTP GET request with stdnet TCP stream. The source for this listing is in this file. Some remarks about listing 8.6. On line 10, we specify HTTP 1.0. Using this version of HTTP ensures that the connection is closed when the server sends its response. HTTP 1.0, however, does not support keep-alive requests. Specifying HTTP 1.1 actually confuses this code, as the server will refuse to close the connection until it has received another request, and the client will never send one. On line 13, we include the hostname. This may feel redundant given that we used the exact hostname when we connected on lines 7 through 8. However, one should remember that the connection is established over IP, which does not have host names. When TCP stream connect connects to the server, it only uses an IP address. Adding the host HTTP header allows us to inject that information back into the context. Section 8.4.1. What is a port number? Port numbers are purely virtual. They are simply U16 values. Port numbers allow a single IP address to host multiple services. Section 8.4.2. Converting a host name to an IP address. So far, we've provided the host name rustinaction.com to Rust. But to send messages over the Internet, the IP, or Internet Protocol, address is required. TCP knows nothing about domain names. To convert a domain name to an IP address, we rely on the Domain Name System, or DNS, and its process called Domain Name Resolution. We are able to resolve names by asking a server which can recursively ask other servers. DNS requests can be made over TCP, including encryption with TLS, but are also sent over UDP, or User Datagram Protocol. We'll just use DNS here because it's more useful for learning purposes. To explain how the translation from a domain name to an IP address works, we'll create a small application that does the translation. We'll call the application Resolve. You'll find its source code in listing 8.9. The application makes use of public DNS services, but you can easily add your own with the -s argument. Public DNS providers. At the time of writing, several companies provide DNS servers for public use. Any of the IP addresses listed here should offer roughly equivalent service. 1.1.1.1 and 1.0.0.1 by Cloudflare. 8.8.8.8 and 8.8.4.4 by Google. 9.9.9.9 by Quad9, founded by IBM. 64.6.64.6 and 64.6.65.6 by VeriSign. Our Resolve application only understands a small portion of DNS protocol, but that portion is sufficient for our purposes. The project makes use of an external crate, trust-DNS, to perform the hard work. The trust-DNS crate implements RFC 1035, which defines DNS, and several later RFCs quite faithfully, using terminology derived from it. Table 8.1 outlines some of the terms that are useful to understand. An unfortunate consequence of the protocol, which I suppose is a consequence of reality, is that there are many options, types, and subtypes involved. Listing 8.7, an excerpt from listing 8.9, shows the process of constructing a message that asks, "Dear DNS server, what is the IPv4 address for domain_name?" The listing constructs the DNS message, whereas the trust-DNS crate requests an IPv4 address for domain_name. We are now in a position where we can meaningfully inspect the code. It has the following structure: parses command line arguments, builds a DNS message using trust_DNS types, converts the structured data into a stream of bytes, sends those bytes across the wire. After that, we need to accept the response from the server, decode the incoming bytes, and print the result. Error handling remains relatively ugly, with many calls to unwrap and expect. We'll address that problem shortly in section 8.5. The end process is a command line application that's quite simple. Running our Resolve application involves a little ceremony. Given a domain name, it provides an IP address. Listings 8.8 and 8.9 are the project's source code. While you are experimenting with the project, you may want to use some features of cargo run to speed up your process. To compile the Resolve application from the official source code repository, execute these commands in the console. To compile and build from scratch, follow these instructions to establish the project structure. 1. At the command line, enter these commands. 2. Once the structure has been established, you check that your cargo.toml matches listing 8.8, available in ch8/ch8-resolve/cargo.toml. 3. Replace the contents of src/main.rs with listing 8.9. It is available from ch8/ch8-resolve/src/main.rs. The following snippet provides a view of how the files of the project and the listings are interlinked. Listing 8.9 includes some business logic that deserves explaining. Lines 30 through 33, repeated here, use two forms of initializing a VAC of U8. Why? Each form creates a subtly different outcome. VAC with _capacity of 512 creates a VAC of T with length 0 and a capacity of 512. VAC !0 surrounded by square brackets creates a VAC of T with length 512 and a capacity of 512. The underlying array looks the same, but the difference in length is significant. Within the call to recv_from at line 58, the trust-DNS crate includes a check that response_as_bytes has sufficient space. That check uses the length field, which results in a crash. Knowing how to wriggle around with initialization can be handy for satisfying an API's expectations. How DNS supports connections within UDP. UDP does not have a notion of long-lived connections. Unlike TCP, all messages are short-lived in one way. Put another way, UDP does not support two-way or duplex communications. But DNS requires a response to be sent from the DNS server back to the client. To enable two-way communications within UDP, both parties must act as clients and servers, depending on the context. That context is defined by the protocol built on top of UDP. Within DNS, the client becomes a DNS server to receive the server's reply. The following table provides a flowchart of the process. It's time to recap. Our overall task in this section was to make HTTP requests. HTTP is built on TCP. Because we only had a domain name, rustinaction.com, when we made the request, we needed to use DNS. DNS is primarily delivered over UDP, so we needed to take a diversion and learn about UDP. Now, it's almost time to return to TCP, but before we're able to do that, though, we need to learn how to combine error types that emerge from multiple dependencies. Section 8.5. Ergonomic Error Handling for Libraries. Rust's error handling is safe and sophisticated. However, it offers a few challenges. When a function incorporates result types from two upstream crates, the question mark operator no longer works because it only understands a single type. This proves to be important when we refactor our domain resolution code to work alongside our TCP code. This section discusses some of those challenges as well as strategies for managing them. Section 8.5.1. Issue: unable to return multiple error types. Returning a result of T, E works great when there is a single error type E, but things become more complicated when we want to work with multiple error types. Tip: for single files, compile the code with rustc file name rather than using cargo build. For example, if a file is named io-error.rs, then the shell command is rustc io-error.rs &/io-error.exe. To start, let's look at a small example that covers the easy case of a single error type. We'll try to open a file that does not exist. When run, listing 8.10 prints a short message in Rust syntax. We won't win any awards for user experience here, but we get a chance to learn a new language feature. The following listing provides the code that produces a single error type. You'll find its source in this file. Now, let's introduce another error type into main. The next listing produces a compiler error, but we'll work through some options to get the code to compile. The code for this listing is in this file. To compile listing 8.11, enter the cha/misc directory and use rustc. This produces a stern yet helpful error message. The error message can be difficult to interpret if you don't know what the question mark operator is doing. Why are there multiple messages about std convert from? Well, the question mark operator is syntactic sugar for the try! Macro. Try! Performs two functions. When it detects OK of value, the expression evaluates to value. When ERR of ERR occurs, try! returns early after attempting to convert ERR to the error type defined in the calling function. In Rust-like pseudocode, the try! Macro could be defined as Looking at listing 8.11 again, we can see the try exclamation macro in action as question mark. In addition to saving you from needing to use explicit pattern matching to extract the value or return an error, the question mark operator also attempts to convert its argument into an error type if required. Because the signature of main is main question mark result of open close parens comma stdio error, Rust attempts to convert the stdnet ADR parse error produced by parse of IPv6 address into stdio error. Don't worry though, we can fix this. Earlier in section 8.3, we introduced trait objects. Now we'll be able to put those to good use. Using box of dyn error as the error variant in the main function allows us to progress. The dyn keyword is short for dynamic, implying that there is a runtime cost for this flexibility. Running listing 8.12 produces this output. I suppose it's a limited form of progress, but progress nonetheless. We've circled back to the error we started with, but we've passed through the compiler error, which is what we wanted. Going forward, let's look at listing 8.12. It implements a trait object in return value to simplify error handling when errors originate from multiple upstream crates. You can find the source for this listing in this file. Wrapping trait objects in box is necessary because of their size, in bytes on the stack, is unknown at compile time. In the case of listing 8.12, the trait object might originate from either file open or ::1.parse. What actually happens depends on the circumstances encountered at runtime. A box has a known size on the stack. Its raison d'etre is to point to things that don't, such as trait objects. Section 8.5.2. Wrapping downstream errors by defining our own error type. The problem we are attempting to solve is that each of our dependencies defines its own error type. Multiple error types in one function prevent returning result. The first strategy we looked at was to use trait objects, but trait objects have a potentially significant downside. Using trait objects is also known as type erasure. Rust is no longer aware that an error has originated upstream. Using box of dyn error as the error variant of a result means that the upstream error types are, in a sense, lost. The original errors are now converted to exactly the same type. It is possible to retain the upstream errors, but this requires more work on our behalf. We need to bundle upstream errors into our own type. When the upstream errors are needed later, say for reporting errors to the user, it's possible to extract these with pattern matching. Here is the process. 1. Define an enum that includes the upstream errors as variants. 2. Annotate the enum with # derive of debug surrounded by square brackets. 3. Implement display. 4. Implement error, which almost comes for free because we have implemented debug and display. 5. Use map_err in your code to convert the upstream error to your omnibus error type. Note: you haven't previously encountered the map_err function. We'll explain what it does when we get there later in this section. It's possible to stop with the previous steps, but there's an optional extra step that improves ergonomics. We need to implement std_convert_from to remove the need to call map_err. To begin, let's start back with listing 8.11, where we know that the code fails. The code fails because ::parse of IPv6 ADR does not return a stdio error. What we want to end up with is code that looks a little more like the following listing. Define an enum that includes the upstream errors as variants. The first thing to do is to return a type that can hold the upstream error types. In Rust, an enum works well. Listing 8.13 does not compile but does do this step. We'll tidy up the import slightly though. Annotate the enum with #derive of debug surrounded by square brackets. The next change is easy. It's a single line change, the best kind of change. To annotate the enum, we'll add #derive of debug surrounded by square brackets as the following shows. Implement std fmt display. We'll cheat slightly and implement display by simply using debug. We know that this is available to us because errors must define debug. Here's the updated code. Implement std error. Here's another easy change. To end up with the kind of code that we'd like to write, let's make the following change. The IMPL block is, well, we can rely on default implementations provided by the compiler, especially terse. Because there are default implementations of every method defined by std error, we can ask the compiler to do all the work for us. Use map_err. The next fix is to add map_err to our code to convert the upstream error to the omnibus error type. Back at listing 8.13, we wanted to have a main that looks like this. I can't offer you that. I can, however, give you this. This new code works. Here's how. The map_err function maps an error to a function. Variants of our upstream error enum can be used as functions here. Note that the question mark operator needs to be at the end. Otherwise, the function can return before the code has had a chance to convert the error. Listing 8.14 provides the new code. When run, it produces this message to the console. To retain type safety, we can use the new code in the following listing. You'll find its source in this file. It's also possible to remove the calls to map_err, but to enable that, we need to implement from. Implement std convert from to remove the need to call map_err. The std convert from trait has a single required method, from. We need two IMPL blocks to enable our two upstream error types to be convertible. The following snippet shows how. Now, the main function returns to a simple form of itself. The full code listing is provided in listing 8.15. Implementing from places the burden of extra syntax on the library writer. It results in a much easier experience when using your crate, simplifying its use by downstream programmers. You'll find the source for this listing in this file. Section 8.5.3. Cheating with unwrap and expect. The final approach for dealing with multiple error types is to use unwrap and expect. Now that we have the tools to handle multiple error types in a function, we can continue our journey. Note: this is a reasonable approach when writing a main function, but it isn't recommended for library authors. Your users don't want their programs to crash because of things outside of their control. Section 8.6. MAC addresses. Several pages ago, in listing 8.9, you implemented a DNS resolver. That enabled conversions from a hostname such as rustinaction.com to an IP address. Now, we have an IP address to connect to. The Internet Protocol enables devices to contact each other via their IP addresses. But that's not all. Every hardware device also includes a unique identifier that's independent of the network it's connected to. Why a second number? The answer is partially technical and partially historical. Ethernet networking and the Internet started life independently. Ethernet's focus was on local area networks, or LANs. The Internet was developed to enable communications between networks, and Ethernet is the addressing system understood by devices that share a physical link, or radio link in the case of Wi-Fi, Bluetooth, and other wireless technologies. Perhaps a better way to express this is that MAC, short for Media Access Control, addresses are used by devices that share electrons. Figure 8.3. But there are a few differences. IP addresses are hierarchical, but MAC addresses are not. Addresses appearing close together numerically are not close together physically or organizationally. MAC addresses are 48 bits, or 6 bytes, wide. IP addresses are 32 bits, or 4 bytes wide, for IPv4, and 128 bits, or 16 bytes, for IPv6. There are two forms of MAC addresses. Universally administered, or universal addresses, are set when devices are manufactured. Manufacturers use a prefix assigned by the IEEE Registration Authority and a scheme of their choosing for the remaining bits. Locally administered, or local addresses, allow devices to create their own MAC addresses without registration. When setting a device's MAC address yourself in software, you should make sure that your address is set to the local form. MAC addresses have two modes, unicast and multicast. The transmission behavior for these forms is identical. The distinction is made when a device makes a decision about whether to accept the frame. A frame is a term used by the Ethernet protocol for a byte slice at this level. Analogies to frame include a packet, wrapper, and envelope. Figure 8.4 shows this distinction. Unicast addresses are intended to transport information between 2 points that are in direct contact, say between a laptop and a router. Wireless access points complicate matters somewhat but don't change the fundamentals. A multicast address can be accepted by multiple recipients, whereas unicast has a single recipient. The term unicast is somewhat misleading, though. Sending an Ethernet packet involves more than 2 devices. Using a unicast address alters what devices do when they receive packets, but not which data is transmitted over the wire or through the radio waves. Section 8.6.1. Generating MAC addresses. When we begin talking about raw TCP in Section 8.8, we'll create a virtual hardware device in Listing 8.22. To convince anything to talk to us, we need to learn how to assign our virtual devices a MAC address. The MacGen project in Listing 8.17 generates the MAC addresses for us. The following listing shows the metadata for that project. You can find its source in this file. The following listing shows the MacGen project, or MAC address generator. The source code for this project is in this file. The code from listing 8.17 should feel legible. Line 25 contains some relatively obscure syntax, though. This code coerces the 2 flag bits described at figure 8.3 to a state of 1. That designates every MAC address will generate as locally assigned and unicast. Section 8.7. Implementing state machines with Rus enums. Another prerequisite for handling network messages is to be able to define a state machine. Our code needs to adapt to the changes in connectivity. Listing 8.22 contains a state machine, implemented with a loop, a match, and a Rust enum. Because of Rust's expression-based nature, control flow operators also return values. Every time around the loop, the state is mutated in place. The following listing shows the pseudocode for how a repeated match on an enum works together. More advanced methods to implement finite state machines do exist. This is the simplest, however. We'll make use of it in listing 8.22. Making use of an enum embeds the state machine's transitions into the type system itself. But we're still at a level that's far too high. To dig deeper, we're going to need to get some assistance from the OS. Section 8.8. Raw TCP. Integrating with the raw TCP packets typically requires root or superuser access. The OS starts to get quite grumpy when an unauthorized user asks to make raw network requests. We can get around this on Linux by creating a proxy device that non-super users are allowed to communicate with directly. Don't have Linux? If you're running another OS, there are many virtualization options. Here are a few. The Multipass project, multipass.run, provides fast Ubuntu virtual machines on Mac OS and Windows hosts. WSL, the Windows subsystem for Linux, at this URL, is another option to look into. Oracle VirtualBox, virtualbox.org, is an open source project with excellent support for many host operating systems. Section 8.9, Creating a Virtual Networking Device. To proceed with this section, you will need to create virtual networking hardware. Using virtual hardware provides more control to freely assign IP and MAC addresses. It also avoids changing your hardware settings, which could affect its ability to connect to the network. To create a TAP device called tap-rust, execute the following command in your Linux console. When successful, IP prints no output. To confirm that our tap-rust device was added, we can use IP tuntap list subcommand as in the following snippet. When executed, you should see the tap-rust device in the list of devices in the output. Now that we have created a networking device, we also need to allocate an IP address for it and tell our system to forward packets to it. The following shows the commands to enable this functionality. The following shows how to remove the device once you have completed this chapter by using del rather than add. Section 8.10, Raw HTTP. We should now have all the knowledge we need to take on the challenge of using HTTP at the TCP level. The MGET project, MGET is short for manually get, spans listings 8.20 through 8.23. It is a large project, but you'll find it immensely satisfying to understand and build. Each file provides a different role. Main.rs, or listing 8.20, handles command line parsing and weaves together the functionality provided by its peer files. This is where we combine the error types using the process outlined in section 8.5.2. Ethernet.rs, or listing 8.21. Generates a MAC address using the logic from listing 8.17 and converts between MAC address types, defined by the small TCP crate and our own. HTTP.rs, listing 8.22. Carries out the work of interacting with the server to make the HTTP request. DNS.rs, listing 8.23. Performs DNS resolution, which converts a domain name to an IP address. Note: the source code for these listings, and every code listing in the book, is available from github.com/rust-in-action/code or manning.com/books/rust-in-action. It's important to acknowledge that listing 8.22 was derived from the HTTP client example within the small TCP crate itself. Whitequark, at whitequark.org, has built an absolutely fantastic networking library. Here is the file structure for the MGET project. To download and run the MGET project from source control, execute these commands at the command line. Here are the project setup instructions for those readers who enjoy doing things step by step with the output omitted. 1. Enter these commands at the command line. 2. Check that your project's cargo.toml matches listing 8.19. 3. Within the src directory, listing 8.20 becomes main.rs. Listing 8.21 becomes ethernet.rs. Listing 8.22 becomes http.rs. And listing 8.23 becomes dns.rs. The following listing shows the metadata for MGET. You'll find its source code in this file. The following listing shows the command line parsing for our project. You'll find this source in this file. The following listing generates our MAC address and converts between MAC address types defined by the small TCP crate and our own. The code for this listing is in this file. The following listing shows how to interact with the server to make the HTTP request. The code for this listing is in this file. And finally, the following listing performs the DNS resolution. The source for this listing is in this file. MGET is an ambitious project. It brings together all the threads from the chapter, is dozens of lines long, and yet is less capable than the request get of URL call we made in listing 8.2. Hopefully, it's revealed several interesting avenues for you to explore. Perhaps, surprisingly, there are several more networking layers to unwrap. Well done for making it through a lengthy and challenging chapter. Summary. Networking is complicated. Standard models such as OSIs are only partially accurate. Trait objects allow for runtime polymorphism. Typically, programmers prefer generics because trait objects incur a small runtime cost. However, this situation is not always clear-cut. Using trait objects can reduce space only because a single version of each function needs to be compiled. Fewer functions also benefit cache coherence. Networking protocols are particular about which bytes are used. In general, you should prefer using a &U8 within square brackets literals, b ellipse surrounded by quotes, over &str literals, which are ellipse surrounded by quotes, ensure that you retain full control. There are three main strategies for handling multiple upstream error types within a single scope. Create an internal wrapper type and implement from for each of the upstream types. Change the return type to make use of a trait object that implements std error error. Use .unwrap and its cousin .expect. Finite state machines can be elegantly modeled in Rust with an enum and a loop. At each iteration, indicate the next state by returning the appropriate enum variant. To enable two-way communications in UDP, each side of the conversation must be able to act as a client and a server. Chapter 9. Time and Timekeeping. This chapter covers understanding how a computer keeps time, how operating systems represent timestamps, synchronizing atomic clocks with the Network Time Protocol, or NTP. In this chapter, you'll produce an NTP, or Network Time Protocol client that requests the current time from the world's network of public time servers. It's a fully functioning client that can be included in your own computer's boot process to keep it in sync with the world. Understanding how time works within computers supports your efforts to build resilient applications. The system clock jumps both backwards and forwards in time. Knowing why this happens allows you to anticipate and prepare for that eventuality. Your computer also contains multiple physical and virtual clocks. It takes some knowledge to understand the limitations of each and when these are appropriate. Understanding the limitations of each should foster a healthy skepticism about micro-benchmarks and other time-sensitive code. Some of the hardest software engineering involves distributed systems that need to agree on what time it is. If you have the resources of Google, then you're able to maintain a network atomic clock that provides a worldwide time synchronization of 7 milliseconds. The closest open-source alternative is CockroachDB at cockroachlabs.com. It relies on the NTP, which can have a worldwide latency of approximately dozens of milliseconds. But that doesn't make it useless. When deployed within a local network, NTP allows computers to agree on the time within a few milliseconds or less. On the Rust side of the equation, this chapter invests a lot of time interacting with the OS internals. You'll become more competent with unsafe blocks and with using raw pointers. Readers will become familiar with Chrono, the de facto standard crate for high-level time and clock operations. Section 9.1, Background. It's easy to think that a day has 86,400 seconds, or 60 seconds times 60 minutes times 24 hours, which equals 86,400 seconds. But the Earth's rotation isn't quite that perfect. The length of each day fluctuates due to tidal friction with the moon and other effects such as torque at the boundaries of the Earth's core and its mantle. Software does not tolerate these imperfections. Most systems assume that most seconds have an equal duration. The mismatch presents several problems. In 2012, a large number of services, including high-profile sites such as Reddit and Mozilla's Hadoop infrastructure, stopped functioning after a leap second was added to their clocks. And at times, clocks can go back in time. This chapter does not, however, cover time travel. Few software systems are prepared for the same timestamp to appear twice. That makes it difficult to debug the logs. There are two options for resolving this impasse. Keep the length of each second fixed. This is good for computers, but irritating for humans. Over time, midday drifts towards sunset or sunrise. Adjust the length of each year to keep the sun's position relative to noon in the same place from year to year. This is good for humans, but sometimes highly irritating for computers. In practice, we can choose both options as we do in this chapter. The world's atomic clocks use their own time zone with fixed length seconds, called TAI. Everything else uses time zones that are periodically adjusted. These are called UTC. TAI is used by the world's atomic clocks and maintains a fixed length year. UTC adds leap seconds to TAI about once every 18 months. In 1972, TAI and UTC were 10 seconds apart. By 2016, they had drifted to 36 seconds apart. In addition to the issues with the Earth's fickle rotational speed, physics of your own computer make it challenging to keep accurate time. There are also, at least, two clocks running on your system. One is a battery-powered device called the real-time clock. The other one is known as system time. System time increments itself based on hardware interrupts provided by the computer's motherboard. Somewhere in your system, a quartz crystal is oscillating rapidly. Dealing with hardware platforms without a real-time clock. The Raspberry Pi device does not include a battery-supported real-time